In video 32 on the Foundations of the Computational Economics course, we will look again at the CompEcon model, but this time we will work with the discretized choice rather than solving on the grid as in video 30. This video is also a practical video, so we will code up the new solver, the solver with discretized choice, right here in the video. Just to remind ourselves, the cake eating problem is the problem of deciding of how much of the cake to eat, given the initial size of the cake denoted W0. In each period t, the CT is the consumption that has to come of the, the consumption of the cake, and this consumption has to be found in each period up to infinity. This is an infinite horizon version of this problem that we are considering. Now, the motion rule is very simple, right? So whatever is not eaten in period t, so the difference between the size of the cake in period t and the consumption in period t is left for the next period, and the problem repeats. Let's look at the Bellman equation, which nicely summarizes the any dynamic model. Let's remind ourselves that the Bellman equation is essentially an expression for the value function, which is the maximum attainable utility in this problem, and this is a recursive representation of the maximization that we have at hand over many different many periods. So by just looking at the arguments of the value function over here, we can see that the state space of the problem is composed of just one variable, that's the size of the cake in period t. The choice space appears here under the maximum, and the only choice variable in this problem is the consumption level, and as you can see, it has to be between 0 and the current size of the cake, so it's the choice and the choice set that we have over here. The instantaneous payoff is given by the log utility function of the consumption. So this is what the decision maker obtains in every time period. And then the future is weighted against the current consumption with the discount factor beta, which is also written here. Now, if the model was stochastic, so it had some random elements, then we would also have the expectation here. But since we don't have it, then we know that this problem is completely deterministic. And in addition, you can see that the arguments of the value function appearing here inside of the Bellman equation essentially gives us the motion rule for the state variable. And that's, as we already mentioned, is basically whatever is not eaten in period t is left for period t plus 1. The optimal consumption policy function, which is the function of how much to consume depending on how much of the cake you have left in period t, is simply given by the argmax. So these are the points where the maximum is attained for the Bellman equation. So we just went through all of the necessary components of a dynamic model. We've said that state variables, the state space is given by the size of the cake Wt. Decision variables are, there's only one, the amount of consumption. The instantaneous payoff is given by the utility function, which is a log of c in our case. Discounted, times over discounted utility. There is a discount factor beta as well that we saw in the Bellman equation. And the motion rules are given by this simple recursive expression. Now, in order to solve the problem, we have to find the value function and the policy function. And this is what we are doing by solving the Bellman equation. We of course take the numerical approach to solving this equation, at least even though we already know that this particular model has an analytical solution that we saw in video 30, but still. And so how do we approach it numerically? Well, we will implement the value function iteration solution method as well. And this is basically entails us to finding the fixed point of the functional equation given by the operator t, which is the Bellman operator, right? And the way it works is that we feed some value function to the operator, and it appears here, and then we calculate this expression to get the output of the operator, which is the new value function essentially. All right, and this gives us the VFI algorithm. We start with arbitrary guess of the value function. Yeah, soon we'll actually talk in details about the theory of dynamic programming, and then we'll see why exactly it works. For on each iteration I, we just compute the new value of the value function given by the operator by the Bellman operator, and in the same time we can compute the policy function by computing this argmax. Now this can be repeated until convergence, exactly as we did for the on the grid solution. Now remember that we also had to stop and think about how to implement the Bellman operator numerically, and as before, the first step is to discretize the state space W. So we will work with a grid defined over the state space of W with some upper bound, which we have to choose before we even start solving the model. I'm going to denote the grid with this vector notation. That's all the points. And essentially, what we have to do is we have to calculate the value function in the iteration I on the grid, taking as input the value function calculated at the previous iteration. And here, on the grid means basically for all possible values, for all points on the grid. That we have to do it. And in principle, we could form a loop over all of the points, but similar to what we did in the on-grid solution, we will vectorize this calculation instead to speed it up, essentially. The key point here is that given the value function, which is already calculated on this grid, we have to be able to calculate it in these points. And these points don't necessarily lie on the grid of W, as you can see here, unless C, is measured in the units, which is exactly the difference between the points on the grid here. We will fall off the W grid, and therefore we have to interpolate the already computed on the previous iteration value function V, and this is where the interpolation really comes in. Remember that on the grid we replaced the consumption was taken as a difference between the grid points, and we could rewrite the model so that the next period size of the cake is the choice rather than consumption. But if you remember, that led to a very inaccurate solution of the problem. So I've just copied the code from video 30 here so that we can compare it to the new one. But here is the analytical solution that we also derived in video 30. And the existence of this analytical solution makes the cake eating problem really convenient for testing different approaches to solve it numerically. Right, so I've written a little function to visualize the differences between the analytical solution and the numerical solution. Here are the formulas for the analytical one. We'll have a grid coming from the model. The function takes the model as an input variable, and this is implied. This is supposed to be a cake-eat model. There will be a dense grid for analytical solution. We first solve the model and then make a 1 by 2 plot here, and value function and policy functions, and we will plot into ax1 into first axis. We'll plot the value function and the analytical value function, and in x2 we'll plot a policy function, analytical policy function. Now legends and show. So this is a very simple visualization. Let's not forget importing the matplotlib here, and then we can run this run this function with the cake on grid model, which is M1. And these are the pictures that we saw before. Very inaccurate, right? So the solution has to be the optimal policy function has to be a linear function of the cake size, but instead we have these two giant steps. And as we saw before, adding points on the grid there where we solve it helps it a little bit, but not too much. Both the optimal policy is really ragged, and then the value function also deviates from the analytical value function quite a lot. Okay, so let's try to help it. Let's try to improve this situation by running a more accurate solver. So what do we do here? Rather than trying to avoid interpolation by rewriting the problem in terms of the next period choice, we will discretize the choice variable, okay? So that we still don't have to solve for the optimal choice as using any iterative operations, maximization operations, which is also possible, right? So in principle, we could for each point of the state space, for each size of the cake, we could run an optimizer and find the optimal consumption for that particular size of the cake. But instead, today we will discretize the choice. And so we will have, as before, sort of a matrix where we take a maximum along one of the axes. But we'll have to use interpolation so that the already computed next period value function can be interpolated at the right points. So how will that go? We will have to control for the grid over state space and separately, right, from the grid on the choice space, and that's going to be the biggest difference in the code. VFI will look pretty much the same. We will discretize the state space. We will discretize the decision space with some different grids. So vec D here, and usually, the maximum consumption is the size of the cake itself, and so the upper bounds can be equalized. So see what's happening here. So we will choose the consumption level from the collection of the points on this grid and plug it into here, and then whatever number is here, we need to be able to calculate the value function there. So the plan of action is to compute the value and the policy function point by point on the state grid, and then find the maximum of the points over the choice grid, and only sort of look at those points which correspond, satisfy the condition of the choice set. So in each iteration, what iteration does is computes the value function on the state space grid, and then for the iteration, for the next iteration, we will have to interpolate, like I already said. Okay. All right, so here's the task. We will have to code up the new version of the cake eating model. And so let me go to the normal notebook mode here. And because the models are so similar, I'll just actually start with the code of the solution on the grid. And first of all, copy it over here. We are writing a new class, right? Class to implement the cake eating model with discretized choice. Let's think about the differences. First of all, well, as pointed out here, the biggest difference is that we are treating the grid over the state space and the grid over the choice space separately. So let's have another variable for the number of points in the choice grid, where we will reuse W bar as the upper bound. So let me call this nch grid. So everything to do with choice will have the ch in the variable names. And let's make this grid a little bit denser than the grid of the state space. And something very similar will appear for all of this choice grids. So nch grid, number of grid points for choice grid. And then we will create the choice grid similar to what we did with the state grid. So now this is grid for state space, and this is grid for decision space. self-ch grid is linspace. We also avoid 0 just in case here, and ch grid. All right. So these are all of the changes in the initializer. Now let's think about the solver before we go to the Bellman equation. See, the solver is implementing VFI solution method, and it is calling Bellman operator, in a loop many times and updating the value function and checking for convergence. This is all going to be exactly the same. So really, the changes are in the Bellman operator that we need to implement. Bellman operator V0 is one-dimensional vector of values on state grid, let's say, because they are on the state grid. We're solving the Bellman operator on the grid of discretized state space. And things are going to be a little bit different here. So remember, before we had the difference between the state grids to denote the choices, but now choices are going to be coming from the choice grid itself. Except I still want to keep them in columns. So I as before, I want to have choices over here, choices in columns. This is choice, and then state spaces in the rows. Okay, and then we will take a max to calculate the answer in the Bellman equation. So we will calculate everything inside of this bracket here as a matrix with states on the horizontal and choices on the vertical. So choices in different different values of choices in different rows, and different points of the state space in different columns. Okay, I'm working over here. All right, so I want to create, from this choice grid, I want to create a column vector. And to do that, I'm going to use this new axis command from NumPy. The choice grid is a one-dimensional vector, but now it's a column vector. Okay, once I know the choices, let's think about what we really need. We want the matrix of V1 to be equal essentially an npi log of choices plus self beta. I'm just implementing the Bellman equation times the V0 calculated at the right points. And what are the right points? Well, the right points are whatever I had today. And okay, let's say this is what I had today, and this is just going to be the state grid, right? This is going to be the grid, and this must be one-dimensional, which is like a row vector. And so this is what's left for tomorrow, right? And these are the points where I have to calculate the V0. Well, V0 is only defined, this is just basically a vector of values, also one-dimensional. So this is like the functional values in the points where we know the function we've calculated, but we have to calculate it in between of these grid points. So instead of V0 here, we need to interpolate. So let me say this interp is going to be the interpolation function. I'm going to go back to the notebook with interpolation to grab the interpolation method from here. We need to import the scipy interpolate, and let's, for starters, do the simplest interpolation possible, which is going to be linear interpolation using this interpolate interp 1D function. So this is going to be my interpolation function. Okay, what sort of data do I have to give it? Well, the value function is defined on the grid over the state space, and the values are given to the Bellman operator in this list of V0, in the array of V0. Okay, so this is my interpolation. So now these are going to be the values in the next period. In the next period. the size of the result of the interpolation is going to repeat the size of these arguments, and the arguments are going to be a matrix, right? Because this is a row vector subtracted from the the column vector subtracted from the row vector. So because of the broadcasting, this subtraction will actually produce a matrix with all possible points in the state space on the in different columns, and all possible values of the choices in different rows. Okay, so is this what we need? Because then we will just take this to be the A max of the mat V1 ln x is 0, and we will not keep dimensions there to produce a flat one-dimensional array again. And the policy, well, the policy is not the difference anymore, right? The policy is just C, which is here, and we will take only the values which maximize this expression. So we'll take the argmax. Okay, so this is the end. But let's see what else did we do in the on-grid solution. We had this mask to mask off the infeasible choices. Well, do we have to do the same now? Let's think about it. So it could be that W is small, right? So for the points of the state space grid which are small, we could actually subtract something which is larger than them, and that would actually break the computation, because now we would have something negative here. And we go immediately into the extrapolation domain, right? But even more, the value function looks something like this. And actually, that's because of the log utility. There's no value that we can assign to the negative consumption, or the negative size of the cake, rather. The value function is a function of the size of the cake. And therefore, we have to prevent this to be calculated for negative values. How do we do that? Well, now let's see how we did this before. We initialized the mat V1 with minus infinity, and then we only put into the admissible combinations of size of the cake and the consumption. Only there we've put this expression. Well, we could do it the other way around too. So we calculate this for everything. Okay, so we do allow for extrapolation. We need to allow for extrapolation here then. But then for the points where C is greater than W, okay, we can say these points, they have to be equal the negative infinity. So they are never chosen in the in this maximization step down here. So these are infeasible choices. Okay, now how do we allow for extrapolation? We can go back to the approximation and look at the help of the interp ID, which was just here a minute ago. There. Remember, we looked at this in the previous video. The bounds error is what we need to control. So bounds error argument should be false. We don't want to bound it, and we need to provide the field value, the extrapolation extrapolate. Is this correct? Yeah. Okay, so now this interpolation function will actually allow for extrapolation for the negative values. Well, using the last whatever was the last segment in the linear approximation of the value function, but we will replace this extrapolated values with minus infinity. I believe that's all we have to do. So let's try to run this. Well, by creating the model. And solve. Okay, there are some problems. NP is not defined. This is terrible. Import numpy as NP. And here we are. So this is going to be V and P that is produced by the solver, right? The value and the optimal consumption policy. And maybe we can just plot M grid. On the grid, we can plot the value, for example. Oh, why don't we do both? Didn't we do plots already? Over here? Oh. Oh, something is wrong. Can't believe I keep losing the import of the important libraries. Okay, so there's that. Okay. Here we are. We need PLT show to separate two graphs. Yes, that looks like it. Not too impressive, isn't it? Still very far from the diagonal, but at least we're getting a solution and we can work with it. So the class is finished, and let's go on to testing. So I have some code here to compare the on-grid solution and the just nearly coded the discretized solution. And to compare, we will create two different objects, right? One object will represent one model, one approach. The other one is another model. Let's make sure that they have the same parameters. Beta is 0.9, W bar, and the number of grid points, where, of course, here we need another parameter, number of grid points in the choice grid, and let's actually keep it 50 as well, and we'll check against the analytical solution. Okay, so what do we have here? The on-grid solution is pretty poor. You can see that it only has whatever 2 steps here, but look at this. This one is exactly the same. Is it? Completely identical. So what's going on? Well, we are using 2 independent grids over the choices and states. But of course, if they have the same number of points, they're essentially the same grid. And therefore, we're getting something which looks more or less the same. So one way to deal with that, or to address that, is to increase the number of grid points on the decision grids. So then we get something more that more looks like this testing graph here. Right, we get more steps essentially. Why is that? Well, that's because we have more levels of the consumption of the choice grid. So more possible levels of consumptions. And then, of course, you know, the reason for having steps here is because we have basically discrete levels of consumption that we can name to be the optimal ones for particular intervals of wealth, or I'm sorry, of the cake size. Now, what's interesting is that if we decrease beta, say to 0.8, look, even this solution, the on-grid solution, becomes much more accurate. And the discretized solution is becoming, you know, pretty good, or, well, not pretty good, but much better than before. So it depends on the value of the parameters. What's going on? So here, as we change beta, then the slope of the analytical solution changes, and you know, different slopes can be approximated with the stepwise functions better or not as good. So let me go back to the original, and let's think about what else we can do. So how to increase accuracy? increase the number of grid points, both in state space and especially in the choice space. Let's try to increase the number of grid points in the state space, and I'm making them really detailed now. With 500 points in the state space, you can see that even on the grid solution is becoming much more accurate, and you can see how the value function is really approaching the analytical one. Even more so over here. So we still have twice more points on the grid for the choices, and therefore steps are smaller, and the value function is also much closer to the true one. Okay, but this is costly, of course. Can we do what else can we do? Optimize the use of the grid points in the choice space by accounting for the constraints of the model. Let's try to think about what that means. Well, see, when we are solving on grid, then because we don't have this additional degree of freedom of how to model choices, then there is not much to do. The difference between the grid points of the state grid is just going to be what it is. Now, for the choice grid, I guess a little picture would help. If this here on the horizontal is wealth, and on the vertical is choices, like in our matrix, what happens is that every time the choice is larger than the state, this is the area which we're not using in the calculation of the maximum at all. Think of this as what we have here, right? So half of the matrix that we have, we are replacing with minus infinity, essentially. So looking at this picture here, it's like we're creating the matrix, and then half of the matrix is filled by minus infinity. So we are losing half of this grid points that we have. Could we sort of compress all of the grid points into this area where they're useful? Let's try to do that. So how would I do that? This C is the column vector and the row vector, and then I'm using this a matrix. So let me first make it a matrix explicitly. You know what? I'm not going to do it this way. What I'm going to do is I want to repeat the. I want to create a matrix out of C. What's the easiest way to do it? Let's say C over here in line 19. That's a column vector. So if I take a column, a row vector of zeros, right? So how many zeros? I need the number of zeros the same number as the n grid, and I want this to be a row vector, and I want to add C to this. Okay, I want a matrix of consumption values. Let's just check that I'm actually having what I want here. I'll put the testing code right in this cell. So this is going to be cake discretized. But let me say that n grid equals, say, 5 and choice grid equals 6 to keep it small. And then I want to say solve, but max iter, let it be just 1. Okay, so here we go. This is the still can't show it really nicely. Oh, how about that? So here's the matrix of C's, right? It has 1, 2, 3, 4 points in the horizontal direction, so 4 columns, and they correspond to the points in the state space. And then it has 1, 2, 3, 4, 5, 6 rows, which correspond to the number of points in the choices. All right. And as you can see, the choices are essentially repeated, right? So different choices. This is almost 0. This is 2, 4, 6, 8, and 10. All right. So that's the top of this matrix, which is essentially lost, because here the value of the cake, the size of the cake, is going to be very small. So what if we multiply this whole column by the fraction that the size of the cake has in the maximum amount of cake? So essentially I want to multiply this by 1, okay? And this I want to multiply by something really small. Let's try to do that. I want to multiply C column by column. Let me think how to do that. Well, we're just going to multiply, not like matrix multiplication, but multiplication with broadcasting, and then it will be element by element. So self grid divided by self max W, W max, W bar. Okay, let's see what we have now. So this is the fraction that the grid point has within the upper bound. So over here, let me just actually print it as well to make it more explicit. Look, this is a tiny fraction. This is about 1/3. This is about 2/3, and this is exactly 1. And we are multiplying the C matrix that we saw before by this number. So this here doesn't change at all. This here is now multiplied by 0.6, and you can see that that the range in this next to last column is from a tiny amount up to about 6, right? The upper bound is 10, so 2/3 here is the upper bound of the consumption choice, okay? And everything above that we don't even include into consideration. Why? Well, because that would be replaced by minus infinity anyway over here. And so in the first column the numbers are really tiny. So this is like 1, 2, 3, 4, 5, 6 points of the grid of choices, but they are compressed to fit under the current value of the size of the cake, which is tiny. So all of these numbers, you know, the smallest one is times 10 to the minus 33. Okay, potentially there are some numerical issues there, but let's hope they will not be crucial. Now this plus C doesn't look all that well, so instead we can say C plus equal and then this vector. So this is what this means, of course, is that we're taking C, adding this part, and then saving it back to C. And similarly here you can just do this. So this we can say scale choices to ensure C is less than W. Okay, we're almost done, but now remember when we calculate the policy function, now we are indexing into C, and C is after this change, C is a matrix. So we have to be careful about how to index it here. And what's the right way to do it? So these are indices of the values of C that maximized the Bellman equation. And in the matrix, they have to be on the second axis, right? So the first number in this vector has to correspond to the first column, and the second number has to correspond to the second column of the C matrix. So I think what I need to do is to say a range of the self W bar. And so I'm providing essentially just it should be a second coordinate. So I'm providing the second coordinate that will take all the values from 0 to the last one. Okay, and something is not very good here. Let's see. Not broadcastable output operands with shape 6.1 doesn't match the broadcast shape 6.4. Where's this? It's right here. Well, I guess I was too quick on saving the space. How about now? Shape mismatch. Self-payment. This, okay. Indexing arrays could not be broadcast together with shapes 4 and 10. Yes, of course, this shouldn't be W bar. This should be N grid. That was a mistake. No convergence. Maximum number of iterations achieved. Well, of course, because we have only one. And like this, things look better. So let's try to look here. Oh, I should have corrected the... Let's go back to the small case. Yeah, look at this. So that's the same, and we can actually comment it out now. But the solution here is a lot less stepwise, right? Instead, it is a lot more like the analytical one. So if I make even fewer number of points, oh no, that's, you can see that, you know, the nature of the mismatch of deviations completely changed here. And I've changed the code, but it would be actually better to include some sort of a switch. So let's try to include the switch. Let's call it an optim choice, and let's say this is going to be no. Let's make it true by default. Optimization of the choice grid. That's what it means here, and we'll make it into another attribute, and then let's just change this here to be able to turn it off. So if choice optimization is done, else we should have just the normal what we had before. All right. But now if cake discretized and optim yes, there we go. So as you can see, it helped greatly. So even with a small number of points in the choice grid, the fact that we are compressing the grid and ensuring that the constraint is satisfied allows us to greatly improve the accuracy of the solution. So let's compare the two. Look at this. That's the same number of grid points, but with the optimization, the solution is a lot closer to the solution, to the analytical one. And the same thing goes for the value function. So it doesn't deviate here. And of course, the value describes the optimal choices. And therefore, because the optimal choices are wrong, then the value function is wrong as well. I wonder if we can make it a little bit better by actually including the first point here. It is excluded because it is kind of artificial, right? But no, we can add it, and then it is plotted here a little bit better. All right, is this all? So what's the conclusion? The conclusion is that, you know, when writing the code, taking into consideration the properties, the theoretical properties of the model, helps you write a better code, helps you write a more efficient code in the end. What else we could do? We could relocate the state grid points towards the areas of the higher curvature of the value function. The idea here is that, see, we're still missing some value here. So, and you can see how this, you can almost observe the kinks over here. And these kinks will disappear if we include more grid points. Say we'll go to 100. See, it becomes much more accurate, and also the kinks disappear over here. And in order to, but something appeared here. That's actually very funny. But in order to try to make the approximation better, where the curvature of the value function is higher, we could simply put more grid points into that area where the curvature of the value function is higher. And then, of course, we only used the simplest interpolation technique, and instead we could use a more sophisticated approximation technique, like, for example, Chebyshev polynomials, which would probably fit because the function is so smooth, or at least it appears to be very smooth. Or maybe the you know, quadratic or cubic splines could be applied as well. All right, that's it for this video. See you next time.